Okay. Hi, everyone. Welcome to Extremal and Probabilistic Combinatorics webinar. It's a pleasure for us to have Matthew Jenssen to give a talk today. He'll talk on a proof of the upper matching conjecture for large graphs. As usual, during the talk, if you have questions, please write them in the chat. And otherwise, at the end of the talk, there will be time to ask questions. Okay, Matthew.
Hello, everyone. Thank you all for joining. Yeah, I've got the chat up here right in front of me, so feel free at any point to just ask me a question, and I should see it on my screen. So yeah, I want to talk about something called the upper matching conjecture, but to start with, I actually want to introduce two models of a gas in statistical physics. So you might wonder, why on earth would I want to do such a thing if I'm talking about matchings and graphs? But these two models and the tools used to analyze these models provide a lot of the intuition and tools that we'll use in the graph theory setting as well. So the first model I want to talk about is called the Canonical Ensemble. And I want you to imagine a fixed number of particles in some sealed box. So these particles are flying around, but there's a fixed number of them. And I want you to think of these particles as having some kind of mass. So the only constraint I'm going to put on them is that they can't overlap. So in the absence of any other information, there's no real reason to assume that any one configuration is more likely than any other configuration. And so I might as well assume that I have the uniform distribution. More formally, what you do often in statistical physics is look for the entropy maximizing distribution, which in this case is precisely uniform. Here, entropy is precisely the normal probabilistic definition of entropy that you're used to. But in the continuum, even this very simple model can be quite intractable and difficult to analyze. So often what you do, I sort of gave it away, I hadn't prepared my slides correctly, is discretize space and think about these particles as constrained to be living on some vertex of a graph. Hopefully this pointer works. Okay, and so now how do I encode the condition that these particles don't overlap? That's just the condition that they don't share an edge between them in this graph. So that's precisely an independent set in my graph, a collection of vertices which share no edge between them. And so now the canonical ensemble in a graph G is the following probability distribution on independent sets of a fixed size, let's say K. I just choose one uniformly at random. Okay. The second model of a gas I want to describe is called the Grand Canonical Ensemble, very fancy name. But now all I do, instead of fixing the number of particles in my box, what I want to do is I want to fix the average number of particles in a box. So I'm going to suppose I have this, oh, that wasn't supposed to happen. I'm going to suppose that I have some small gray box here living inside a much larger region. And this box is great because it can exchange particles with the outside world. It's permeable. And so now I'm not fixing the number of particles in my box, I'm fixing the average number I expect to see in my box. And here I'm restricting to a discretized setting to make life easier for myself again. And I can ask, what's the entropy maximizing distribution now? Entropy maximizing probability distribution on independent sets now in my gray box, which is now a graph G. And this has a special name. It's called the hardcore model on G. And it's as follows: just select some positive parameter lambda. I'm going to tune that lambda so that I get the right average number of particles in my box. And now I'd select an independent set with the following probability, with probability proportional to lambda to the size of an independent set. So let's say if lambda is very large, I'm biasing towards large independent sets. If lambda is small, I'm biasing towards small independent sets. If lambda is 1, this is actually just the uniform distribution on independent sets of any size. Now we're allowed to vary in size. And this normalizing factor here has a special name. If you're a physicist, it's called the partition function. And if you're a combinatorialist, it's called the independence polynomial. So what is it? Of course, it's just the sum over all independent sets I in my graph G, lambda to the size of I, or sometimes it's more convenient to group independent sets according to their size. So the sum over all integers k, the number of independent sets of size k in a graph G times lambda to the k. I should have probably mentioned at the beginning of the talk, these slides should be available on the talk website. So it might be handy to download them, and you can go back and check and remind yourself of notation. I will try and remind you as well with these little comments in gray, and also just feel free to ask me in the chat. Are there any questions so far? Okay, good. So we can also extend these notions to matchings in a graph. So there's another, when we move to the switch our notion from independent sets to matchings, what do we get? This canonical ensemble setting is just a uniform distribution on matchings of a fixed size k. So now I'll choose a matching in a graph with probability 1 over the number of matchings in my graph G. And here MKG is the number of matchings with k edges. And the grand canonical ensemble perspective is the following probability distribution on matchings. Just select a matching with probability proportional to lambda to the number of edges in that matching. So it's the exact same thing, except now I've changed independent sets for matchings. You could just say, a matching is just an independent set in the line graph of a graph G. So we've really done nothing at all, but it's useful to have this notation. And I'll call this normalizing constant in the matching settings the matching polynomial. So here I'm summing over all sizes k, the number of matchings in a graph G of size k, lambda to the k. And in fact, this isn't just of combinatorial interest. Physicists and chemists study this under the name monomer-dimer model. Dimers are used to refer to the edges of this matching, and the uncovered vertices are called monomers. So this is also of interest to physicists as well, not just combinatorialists. Okay. But I'm interested now, not today in physics, but in some questions in extremal combinatorics. So there are some natural questions in extremal combinatorics that arise in these two settings. One of them, for example, is in the grand canonical ensemble. We say, fix some lambda greater than 0, which regular graph on n vertices maximizes these partition functions, either the independence polynomial or the matching polynomial. I should mention that at lambda equals 1, this is a very concrete combinatorial interpretation. At lambda equals 1, this is just the number of independent sets in my graph, or the number of matchings, total number of matchings in my graph. So here you could ask which d-regular graph on n vertices maximizes the number of independent sets or the number of matchings. And the equivalent question in extremal combinatorics in this canonical ensemble perspective is, fix me a k greater than 0, which d-regular graph on n vertices maximizes the number of independent sets of size k, or the number of matchings on k edges. So these are the two questions, two flavors of question I want to focus on today. And since I'm going to be talking a lot about d-regular graphs on n vertices, I'm just going to introduce this notation of curly G dn is the set of all d-regular graphs on n vertices. Okay, so it turns out that the answer to the first question is fairly well understood. So what do we know? The classical theorem of Kahn, and later also strengthened by Zhao, says that if you're a d-regular graph on n vertices, and I give you some lambda, then we have the following upper bound on the independence polynomial of my graph. It's at most the independence polynomial of KDD, which is the complete d-regular bipartite graph, raised to the power of n over 2. Oh. So what this is saying, another way of looking at the right-hand side, is if 2D happens to divide n, then the right-hand side is just the independence polynomial of the following graph. Just take n over 2D copies of KDD. And since the independence polynomial is multiplicative over components, this is also just z of this graph, which I'll give a name. Let's say it's HDN of lambda. So this disjoint union of KDDs, I'll denote by HDN. That's a shorthand. So in other words, let's fix lambda equals 1. What is this saying? Over all d-regular graphs and n vertices, which graph maximizes the number of independent sets? Well, it's this funny graph here, a disjoint union of KDDs. That's the way to get the most independent sets. And in fact, more generally, it maximizes the independence polynomial. I should say recently, there's been a vast generalization of this result by Sa, Sawney, Stoner, and Zhao, which not only deals with graphs with arbitrary degree distributions, not just regular not just regular graphs, but also far more general partition functions than just the independence polynomial. Okay, and we have this complementary result for matchings as well, which says the exact same thing, but for the matching polynomial. So again, what is this saying? If I give you some d-regular graph on n vertices, which graph maximizes the number of independent sets? Sorry, the number of matchings. Well, it's this funny graph HDN, and more generally, it maximizes this matching polynomial. Interestingly, there are a number of different proofs of this fact. You can use entropy methods or Holder's inequality. But the proof of this fact uses something known as the occupancy method, which is a probabilistic method inspired by statistical physics. And it's the only method I know how to prove this theorem. So in this setting, there is something separating the matchings and independent sets. But actually what I'm going to talk about today, the methods I'll be describing to you today work just as well for matchings and independent sets. There's nothing really separating them. But these problems can have different flavors. So the question in the canonical ensemble is much less well understood. And here we just have some conjectures. So there's a conjecture of Kahn that says this very same graph, n over 2d copies of KDD, not only does it maximize the independence polynomial, but it should maximize every single coefficient of the independence polynomial. In other words, it maximizes the number of independent sets of size k for any fixed size k. That's the conjecture. And there's a complementary conjecture, Friedland, Krop, and Markström, that says the very same thing, except for matchings of size k. Again, a disjoint copy of KDDs should be maximizing the number of matchings of any fixed size over all d-regular graphs of size n. And for some reason, this conjecture has been given a fancy name, the Upper Matching Conjecture. And maybe for that reason, it's attracted a little bit more attention than the complementary independent sets question. But I want to consider these questions together. Okay. So just to recap, a slightly heavy slide here, but this is just recapping some progress on these problems. So Carroll, Galvin, and Tetterley showed that for any d-regular graph on n vertices, log of mkg, that's again the number of matchings on k edges, is at most n over 2 alpha log d h of alpha. This is the binary entropy function, and alpha is 2k over n, so that's the fraction of vertices covered by your matching. The exact form isn't really important, but what's important rather is that it matches the number of matchings in this conjectured extremal graph, at least to first order in the logarithm. And later, Ilinka and Kahn improved this as follows to match the correct asymptotics of the logarithm in HTN all the way up to some term which is little o over 1 in D in the exponent. And then later, myself again with Ewan, Will, and Barnaby, managed to get the following upper bound, which is the first upper bound within a polynomial factor of the conjectured extreme. And later, using these same methods, we managed to strengthen it to give the correct answer for all matchings or independent sets of some linear size. So here we need K to be at least some epsilon n. And what we show is that the upper matching conjecture and this independent set conjecture is true for these K, provided your graph is large. And what I want to talk to you about today is sort of filling in this gap a little bit. So along the way, we somehow lost Barnaby. He left mathematics. Maybe he got very tired of this problem. So together with Ewan and Will, we show that there is some epsilon that depends on D. 1 over D to the 4 or something should suffice, such that if your matching is small, then the upper matching conjecture and this independent set conjecture hold. So of course, taking these two theorems in conjunction shows that the upper matching conjecture and this independent set conjecture hold for all graphs large enough as a function of the degree. Okay, so before I go on to talk about some proofs, maybe now would be a good time to pause for a moment and see if there are any questions.
If you have a question, you can write in the chat. I'll unmute you.
Yeah, feel free to write in the chat. Okay. So I was hoping to say something a little bit about both halves of this proof today to justify the title a bit more, but I'll probably only have time really to say something more about this recent work. But if there's time at the end, I'll try and say something about this earlier work as well. We'll see how we get on. All right. So perhaps rather counterintuitively, the key to understanding these questions in the canonical ensemble, where we're interested in independent sets and matchings of a fixed size, it's very useful to go in the complete opposite direction and think back again about the grand canonical ensemble, the hardcore model, and even more than that, to consider a multivariate generalization of the hardcore model. So what do I mean by that? What do I mean by multivariate generalization? If I give you some graph F, what I want to do now is assign each vertex of F some activity lambda V. And I'll let lambda with a line underneath denote the vector of all of these activities. And actually, crucially here, I don't want to constrain lambda V to be positive reals. In fact, I don't need to constrain them to be reals at all. Of course, then I'm going to lose any type of probabilistic understanding of this model. But what I can do is certainly define this partition function that we had before. So what is this partition function? I can sum over all independent sets in my graph F. What am I summing? The product over all vertices in my independent set of lambda sub B. So why is this a generalization of what we had before? Well, if I just set lambda v to be the same quantity lambda for all v, what am I getting here? I'm getting lambda to the size of my independent set, which is precisely this hardcore model partition function we had before. And there's a tool, a very useful tool from statistical physics, used to analyze these types of partition functions, which is called cluster expansion. So I'll give you a little preview of what this is before I give you an overview of the proof. The cluster expansion is just a multivariate Taylor series of the logarithm of this partition function. So here's a little preview of what it looks like. We can't understand all these terms yet, but it'll be useful just to sort of have a rough sketch of what it might be in our mind. So we have the log partition function. I can expand as a sum over some combinatorial object, which I'll call clusters, which I haven't defined yet. Then there'll be some real number associated to that cluster. And then I'm going to take the product over all vertices in this cluster of lambda to the v. So it actually looks surprisingly like the original partition function, except instead of summing over independent sets, I'm summing over these objects called clusters. Okay, but of course we don't really know what that means yet. But let me now at least give you a broad overview of the proof strategy. So here's the theorem again that we're trying to prove. So for any d, there exists some epsilon, again, epsilon being 1 over d to the 4 should do, such that if I have a d regular graph on n vertices, and I want 2d to divide n, then so long as k is sufficiently small, the number of matchings in G and the number of independent sets in G of size k are most what they are in this extremal graph, this disjoint union of KDDs. So here,
Can't hear you, Matt. We can't hear you. Oh, now, can you say something?
One second, something's gone wrong here.
It's good now. We can hear you now.
Ah, you hear me again?
Yeah.
Okay, good. Excellent. I don't know quite what happened there. I just got a panicked message from Zoom saying something had gone wrong on my computer. Okay, so where were we? So the proof strategy is to rewrite these two quantities that we're interested in as the multivariate hardcore partition function ZF lambda for some auxiliary graph F. So I need to build this special graph F. And then I'm going to expand the log of the partition function, which in this case is log of the quantity I'm interested in, as an infinite series via the cluster expansion. So slightly counterintuitively, we're going to expand this thing that we're kind of thinking of as a fixed number. It's just the number of independent sets or matchings of a fixed size in my graph G as an infinite series. And of course, this infinite series is going to depend on the graph G in question. And so then what I'm going to work hard to do is show that this HGN graph optimizes or maximizes the dominant terms in these expansions. So that's the overall picture of the proof. So for the remainder of the talk, I'm going to introduce this cluster expansion first, and then I'm going to show you how to build this auxiliary graph F before we complete the proof. Are there any questions so far? Okay, and please let me know if I suddenly go silent again. Okay, so up here in gray, I kind of have just these reminders of these objects that we're interested in. This is the multivariate partition function, and this is this expansion of the logarithm of this partition function. We don't know what that is yet, but we're going to find out on this slide. So I want you to consider a vector C of vertices in my graph F. So this is just some vector of vertices. And I'm going to build the following graph H of C. I'm going to have a vertex for each vertex in my vector. And I'm going to draw an edge between Vi, Vj, if and only if Vi is not adjacent to Vj in F. And if this resulting graph is connected, I'll call C a cluster. So it's important here that we allow repetitions in this vector. This vector can have arbitrary length. So a good example of a cluster is gamma, or rather than gamma, let me use V. A vertex V, a vertex V, comma, vertex V, 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 V. These are all excellent examples of clusters. Why? Because what's the corresponding graph that we'll build? We have a vertex for each object in our cluster. In this case, they're all V. And do I have an edge between them? The answer is yes, because V is not adjacent to itself in F. So in fact, all of these edges are present. And since this graph is connected, it's a legitimate cluster. So there are infinitely many clusters. And so this sum over clusters in the expansion is an infinite series. So the question of convergence is certainly a non-trivial question, and it's something that we'll have to work hard to think about. Okay, so this is what I meant by this combinatorial object clusters. We'll do an example later just to get more of a handle on it. But first, let me tell you what this coefficient here, lambda sub c, is. It's some real number, and it's some parameter of this graph H of C. It doesn't really matter what it is, but just for completeness, here's what it is. Lambda c is it's the following graph parameter. It's 1 over the number of vertices in this graph, in this case 4 factorial, and then I sum over edge subsets of this graph that contain a spanning tree minus 1 to the number of edges. So why don't we just do this example for this particular graph? What's the self function of this graph here? Well, we're going to have a 1 over 4 factorial, since there are 4 vertices. Then here's a very nice spanning tree, an edge set that contains a spanning tree. So that's got 3 edges. I get a minus 1 to the 3. That's minus 1. Here I get a minus 1 for this edge subset. I get a minus 1 for this edge subset that contains a spanning tree. And then finally, I get a plus 1 for this edge subset. So that was minus 1, plus 1, which equals minus 1 over 12. So it's some real number that depends on this graph. Okay, so that's quite a lot to digest. So let's do an example. Let's think of the simplest partition function we can possibly think of. So why don't I just take my graph F to consist of a single vertex V. And the activity I'll assign to it, I'll call lambda sub v, which I'll just call lambda. So what's the partition function? Well, it's the sum over independent sets, lambda to the size of the independent set. So if I get a 1 from the empty independent set, I probably should have specified that I always consider the empty independent set as the empty set as an independent set of size 0. So I get a 1 plus a lambda for the independent set of size 1. And so now what's the cluster expansion? It's going to be some Taylor series of the log partition function. So in this case, that's just an expansion of log 1 plus lambda. Okay, so let's find out what the clusters are in this case. Well, remember, clusters were vectors of vertices. Here we only have one vertex, so the only vectors at our disposal are vectors v, v, comma v, v, comma v, comma v, and so on. What was this graph HC again? Well, we had a vertex for each entry in our vector, and we had an edge between them if and only if there was no edge between the corresponding edges in this vector. So in this case, I'm just going to get a sequence of cliques. So if we just go back to the cluster expansion, I'm going to get a sum over clusters, which in this case is, I can index just by the number of entries in my vector. So the first term I'll get is whatever this phi of the single vertex graph is, times lambda, times phi of this graph, times lambda squared because we're taking the product of all vertices in my cluster, lambda times lambda, phi of the triangle, lambda cubed, and so on. But of course, we actually know what the Taylor series of log 1 plus lambda should be. It's just lambda minus half lambda squared plus a third lambda cubed, and so on. So in this particular case, we knew what the cluster expansion was a priori. And it's sort of interesting that this tells us what these weird functions of the cliques should be. This is saying that 1 over k factorial, the number of edge sets, sum over edge sets containing a spanning tree in a clique of size k minus 1 to the a should just be minus 1 over k or something. Some funny combinatorial identity that pops out there. Okay, are there any questions on that? Since we're going to be doing a fair amount of cluster expansion, it would be good to make sure we understand that.
I have a question. Why was z lambda equal to 1 plus?
I can't. Is there, Liana, are you trying to speak?
Yeah, you can't hear me?
I can't hear anyone.
Hi.
Okay, maybe it's best. I don't think I can hear people, so maybe it's best to type your questions because I have the chat in front of me here. There are glitches. Have there been glitches in my voice? Can everyone hear me okay? Okay, good stuff. Great. All right, let's crack on. So that's the cluster expansion. And what was step 2 in my proof strategy? The idea was to encode the number of matchings or number of independent sets in a graph as the partition function of some multivariate hardcore model. So that's what I want to show you how to do now. And it's just a little bit easier notationally to work with to do the independent sets case. But if you want, just replace G by its line graph throughout and you'll get the proof for matchings as well. And the following is just a sequence of combinatorial manipulations. But we came across it by actually adapting a cluster expansion in the canonical ensemble in the continuum in the physics literature. But but just to the discrete case. But when translated from the continuum to the discrete case, it's just a sequence of combinatorial manipulation. So let's see what it is. Okay, so again, I have some graph G. It's a d-regular graph on n vertices. And I'm going to define G loop to be G, but with a loop added to every vertex. So perhaps this is G, and this is an example of G loop. And I'll denote the edge set of this loop graph as E loop. Okay, so how are we going to rewrite the number of independent sets of size k in your graph G? Well, let's just sum over all maps from the set K into V, the vertex set of my graph V. And let's just check for every pair whether that gets mapped to an edge of G or not. Remember, I'm looking for an independent set, so every pair better not be an edge of my graph G. So that's what this indicator function is making sure of, that the image of FIFJ is not an edge of my graph G. So what's the role being played by this loop? Well, this is ensuring that I and J don't get mapped to the same vertex. So in fact, this forces this function f to be injective. And so the only terms contributing to this sum are precisely independent sets of size k, and I divide by this 1 over k factorial because I don't care about the ordering of that independent set. So there's just some way of rewriting the number of independent sets. What I can do then is just very simply, let me rewrite this indicator as 1 minus the indicator of the complement event. And now what I want to do is I want to expand this product. So what does that look like? Well, I'm going to get a sum over all edge subsets of k choose 2, once I expand this product, minus 1 to the number of pairs I chose, minus 1 for every time I chose this guy. And I get this product over all pairs in A of this indicator function, that FIFJ is an edge of E loop. So this is just expanding out this product. Now what I want to do is I want to switch the order of summation. And what I'll get is a sum over all maps from K to V of this product of indicators for some fixed A. So what's that asking? That's just asking that every pair in A is indeed an edge of my graph G. But that's nothing more than the number of homomorphisms from A to G loop. So homomorphisms is just number of maps from the vertex set of your graph A to the vertex set of G. The number of those maps which map edges to edges, preserve edges. And here I'm using a slight abuse of notation. I'm using A not only as the edge set, but also as the graph K, A, the graph on vertex set K. So we arrive at this new formulation on the number of independent sets of size K as some sort of inclusion-exclusion of homomorphisms. Okay, so let me just write that up again, except let me do I've done a slight sleight of hand here and just introduce some notation on the fly. TAG is the homomorphism density. So that's just the number of homomorphisms from A to G loop divided by the number of maps there are from the vertex set of A to the vertex set of G loop, n to the k. Is the probability that a random map from A to G is indeed a homomorphism. And to compensate for this n over n to the k, I've just pulled one out front here. So nothing's happened here, I've just introduced some notation and remembered where we got to in the calculation. Okay, so remember the goal is to rewrite this as some partition function of some, as the independence polynomial of some auxiliary graph. And the first thing I want you to notice is that these summands factorize over the connected components of A. So here's an example. Suppose K is 7. So we're looking at subgraphs of K7. And maybe A is the following collection of edge subsets, 2, 3, 4, and this triangle 1, 6, 7. Then the homomorphism density of A simply factorizes over its connected components. So it's the homomorphism density of the triangle, the path on two edges, and a single vertex. And of course, this -1 to the A factorizes in just the same way. So I can split, instead of A, I want to think of a collection of connected subgraphs, compatible connected subgraphs. So what do I mean by that? I'm going to construct the following auxiliary graph. I've tried to draw a picture below the fold in the slide. I don't know if it's helpful. Let me give you the definition first, and then maybe we can stare at the picture. I'm going to build the following graph. It's got nothing to do with G at all. The following graph, independent of G. What are the vertices of the graph? They're connected subsets of the clique on the clique of K vertices. So for example, this triangle would be a vertex of my graph. This path of length 2 would be a vertex of my graph. And I'm going to add the stipulation that there's at least 2 vertices. So this isolated vertex isn't a vertex of my graph. And I'm going to draw an edge between 2 vertices if and only if they share a vertex. So if they overlap in KK. Share a vertex as subgraphs on the clique on K vertices. So that's my auxiliary graph. Maybe I will go below the fold and just, in case it's helpful. Again, here's K equals 7. What are the vertices of F? I get a vertex for every connected subgraph of KK where I remember their labels, if you like. Oh. And I draw an edge between them if they share a vertex, if they share a label. So here there's an edge between this gamma 1 and this gamma 2, because this graph and this graph both have a label 3. There's no edge here because they're disjoint. And all I want you to notice is the very simple fact that an independent set in F is precisely just is in bijection with subgraphs of KK. For example, let me take this independent set consisting of these 2 vertices. That's just the following graph. It's 1, 3, 5, union 2, 4, 8, 2, 4. That should be a 7. So there are these so there's just a bijection between independent sets in my graph F and subgraphs of KK, which is precisely what I want. Here I have a sum over subgraphs on the clique of K vertices. Here I have a sum over independent sets of IF. And what's the summand? Well, I need to tell you the activity I've put on this auxiliary graph F. At every vertex gamma, I'm going to give it the activity -1 number of edges of gamma times its homomorphism density. So F doesn't depend on G at all, but these weights do depend on G. That's where the dependence on G comes in. So what's this product? Well, because of this factorization, it's precisely the summand that I have here. And you might ask why do I restrict to there being at least 2 vertices? Well, I can just throw away isolated vertices after I notice that the homomorphism density of a single vertex is 1. So what I lose out here in the product is just a product of 1s. So I still get the correct contribution. Okay, so just to recap, we've rewritten the number of independent sets of size k as some scaling, which is independent of the graph, as the partition function of some multivariate hardcore model. And now I can hit it with the cluster expansion. So what does that look like? So here's a reminder of what the cluster expansion is. So let's go slowly. Remember, what are the vertices of this auxiliary graph F? They're just some collection of connected graphs. And we've given them these weights. So one thing I want you to notice is, in fact, when gamma is a tree, then this homomorphism density doesn't depend on G at all. We just have this explicit formula d plus 1 over n to the gamma. D plus 1 because G looped is not a D regular graph, but a D plus 1 regular graph. Because if you've partially embedded a tree, how many choices do I have for the next leaf? Precisely D plus 1. So for trees, this is independent of G. And so in this cluster expansion, I can just collect all terms that involve only trees as some function of k, d, and n that doesn't depend on my graph. So some weird function, I don't really care what it is because it doesn't depend on my graph G. Okay, but then what are the next interesting clusters? Well, I better look at the clusters that come from a single triangle, say. Remember, these correspond to vertices of my graph F. And what's the weight? What's the contribution to the cluster expansion of clusters of this type? Well, how many are there? There are k choose 3, since there are k choose 3 triangles in the Clee concave vertices, times the weight, which is the homomorphism density of triangles in G loop, times -1 to the number of edges in the triangle, which is -1 to the 3. So I get this minus k choose 3 homomorphism density of the triangle term. And if I look at contribution from clusters, which is just a 4 cycle in the clique, then I get a similar term except a k choose 4 for the number of ways of choosing the 4 vertices of my clique, a 3 for the number of ways of labeling that 4 cycle, and the homomorphism density of a 4 cycle. And some other terms which I claim are smaller order, which I haven't justified, but supposing that were true, then we can see actually quite vividly here that, remember, this is the log of the number of independent sets of size k, that triangles directly hurt you and 4 cycles only help you. So remember, I'm trying to maximize this quantity. Well, what do? I just want a graph with the fewest triangles and the most 4 cycles. And it turns out that, well, it's not hard to show that a disjoint union of KDDs does exactly that job. Of course, it minimizes the number of triangles, it's triangle free, and it's not hard to show that it maximizes the number of 4 cycles, the homomorphism density of 4 cycles, and moreover, it maximizes it uniquely. If I only graph G that doesn't contain a KDD, you get a little win, and that little win here will kill these smaller order terms here. Okay, so that's essentially the proof. Just analyzing the terms of this cluster expansion. I'm going to skip over this next slide. We might come back to it later. So I've realized we've had quite a few heavy slides. And instead, I just want to talk about convergence. So it hasn't been clear yet why we're using k small. Good question. So I kind of brushed, Wojtek asked a very good question. Shouldn't we have this inequality for the looped version of G? The answer is yes. I kind of tried to sweep something under the rug here. if you want to maximize this, then you in fact want lots of triangles. But as soon as you have triangles, you lose here immediately. So there's a little bit of annoyance where you need to, of course, the homomorphism density of C4s in G loop, if you have triangles, if you can map to a triangle, and that's a legitimate copy of C4 in G loop. But as soon as you have any triangles here, this actually just kills you earlier on in here, since this is a sort of, let me at least make this calculation, why this is sort of the dominant term. What is this? K choose 3 looks like epsilon cubed, n cubed. And the density of triangles will be something like n d squared at most over n cubed. So these cancel, and this looks like epsilon cubed times n. Let me forget the dependence on d. This is going to look like epsilon to the 4 times n. So for epsilon small, this is a dominant term. And then the next dominant term is this, and you can show that the rest here is essentially epsilon to the 5 times n. Great. Okay, so just to finish, let me say something about the convergence, because so far it hasn't been very clear why we need k small. I was just doing cluster expansion and assuming everything converges, which is of course illegal. So we need a nice condition, or we need to verify that the cluster expansion converges. And here we have a very nice theorem of Koteki and Price, which is very much related to the Lovász local lemma. You might sort of recognize the Lovász local lemma type form here, which says that if we can show this following funny condition, that for any vertex, this should be in my auxiliary graph, any vertex in this auxiliary graph, if I sum over all vertices adjacent to it, its activity times some exponential, and it's at most the number of edges. If I can verify this funny condition, then that's sufficient for the convergence of the cluster expansion. It turns out that this just isn't, as written, isn't true. And so what you need to do is, instead of consider individual subgraphs of the Pleat KK, you can group them according to their vertex set. And there's a very nice inequality that says, due to Oliver Penrose, and this is a special case of this inequality, that if I sum all of these homomorphism densities over all graphs A on some fixed vertex set R, and I remember their actual weights, then I get a lot of cancellations. This is at most the sum over spanning trees of the absolute values of these homomorphisms. And this gives me a genuine win because there are far fewer spanning trees than there are connected graphs on a fixed number of vertices. And so this inequality is, slots in very nicely to verifying this Koteki Price condition for convergence. And if you write out and do the calculations, you see that the exact condition you need for convergence is that epsilon is less than 1 over d or something. And so this cluster expansion method is only valid provided k is less than epsilon n, where epsilon is something like 1 over d. Okay, I think I'll end there. Thank you very much.
Unfortunately, Matt can't hear us. So write your questions in the chat box.
So sadly, I can't hear anyone, but I'm assuming even. But if you have any questions, then please write them in the chat. I don't quite know why I can't hear anyone. I have a few slides left. Can I say a word or two about the range Sure. I had some secret slides prepared. I'll just say, yeah, a couple of very quick remarks about this. So yeah, what about the range where k is greater than epsilon n? So there's this method that we use called the occupancy method, which is a probabilistic method, also inspired by statistical physics. And that's what we use to prove this inequality in the grand canonical ensemble, or this inequality on the matching polynomial. And so just to give you a brief overview of that method, you put some constraints on local statistics in this monomodimer model in this case, and then optimize subject to this constraints. But that really lends itself quite well to a stability version. You can say things like, if your graph G doesn't contain any copies of KDD, then in fact, you get a very strong version of this inequality. You get a strict inequality with some, in fact, mg will be exponentially smaller than the optimal graph. And so then the way to switch between partition functions and its coefficients is you can interpret, well, let's say, what's the probability of, now I'm selecting a matching with probability proportional to lambda to the size of the matching. What's the probability that my matching has exactly k edges? Well, that's precisely the number of matchings on k edges lambda to the k over this normalizing, this partition function. So then what I want to do is I want to tune lambda to hone in on this coefficient k, by which I mean choose lambda so that the expected size of the matching in this hardcore model is precisely k. And then using this expression, we can look at the ratio, the number of matchings in the optimal graph of size k, let's say, to the number of matchings of size k and g. This is the ratio of these two probabilities times the ratio of these two partition functions. Well, we know a lot about the ratio of these two partition functions, but what do we know about the ratio of these two probabilities? So this is oversimplifying, but one case is, well, we can just say this probability is at most 1, so I don't care about that. And now the number of, this is just a disjoint union of KDDs. So the number of matchings I see in KDDs is just a sequence of independent variables. And so I can just apply a local limit theorem to say, to lower bound this probability, to say it's something like at least 1 over root n. Which is a lot better than 1 over n. And in fact, this 1 over root n allows you to use the stability result to say that this partition function is at least root n times this partition function, to say it's at least 1. So that was the proof when G doesn't contain any KDDs. There's a bit of trickery when G is sort of 99% KDDs and 1% of some other funny graph, but that's the general idea. Thanks.
Any more questions?
Oh, I can hear you now. Okay. There's no rhyme or reason to this, I don't think.
Okay, so if there are no more questions, let's thank Matthew. And I also received a message from Matas. So after we'll stop the recording, but whoever wants to stay can stay for an informal discussion if Matt doesn't mind.
Yeah, definitely.
So hopefully we can clap now. I assume I can. So I will stop the recording now.